In this lecture, we will see how to design 3-bit synchronous down counter using JK flip-flop. In the previous lecture, we have seen the same counter design using D flip-flop. Now we will see using JK flip-flop. Now down counter means what can be the sequence? Something like this. So if initially 0, then it will goes to 7, then 6, 5, 4, 3, 2, 1 and come back to 0 again. So this is the sequence we require. So 0 to 7 means again it is modulus 8 synchronous down counter. Now again we follow the same steps. So step 1 is we have to find the number of flip-flops required. So the moment 3-bit means we need 3 flip-flops. So this is the number of flip-flops. So what is the maximum count? N is equal to 2 power 3, so 8. So modulus 8. So that is, this is also called modulus 8 synchronous down counter. Right. Next, what is the next step? Next step is state diagram. So what is the state diagram? So from this only we can have the state diagram. So 000 initially. So it will, the next state will be 111, then 110, 101, 100, 011, 010, 001. After 001, it is coming back to the 0 again. So that's why it is called modulus 8 synchronous down counter. Now once we know the state diagram, the step 3 is so choice of the flip-flop. Yes or no? So I already mentioned that we are going to use JK flip-flop. So the choice of flip-flop is JK, and for that flip-flop we need excitation table. So this is the excitation table for this JK flip-flop. That is, when I want the next state as 0 and the present state is also 0, we need to apply 0 and don't care. That is two conditions, 0 0 or 0 1. Similarly 0 to 1 I need to apply these inputs, 1 to 0 I have to apply these inputs, 1 to 1 I have to apply these inputs. So once we know this, so next step is we have to get the minimal expression for this, the flip-flops. How many flip-flops required? 3 flip-flops required. So this is the step 4. So this is the present state and this is the next state, and these are the 3 flip-flops required excitation. So J2 K2, J1 K1, J0 K0. Now how to get these required inputs is, so if I want to get the inputs for J2 and K2, we have to see Q2 present state, Q2 next state. So if I see Q2 present state is 0, next state is 1. So when it is changing from 0 to 1, what is the excitation we have to apply is, see here, 0 to 1. So we have to apply 1, don't care. Similarly 1 to 1, 1 to 1, 1 to 1. So 3 conditions are same. See, if I see here 1 to 1 means we have to apply don't care, 0, don't care, 0, don't care, 0. So 3 conditions are over. The next one is 1 to 0. So 1 to 0, what is the inputs required? 1 to 0 means don't care 1. So don't care 1. Next one is 0 0, 0 to 0, and the last one is also 0 to 0. So what is the excitation table? 0 to 0 means we have to apply 0 don't care. So 0 don't care, 0 don't care, 0 don't care. So this is how we have to fill the other flip-flop inputs also. Next, Q1, 0 to 1. So 0 to 1 means what is the excitation we have to apply? 0 to 1 means 1 don't care. So 1 don't care. Next one, Q1 to Q1, 1 to 1. 1 to 1 means what? Don't care, 0. So don't care, 0. Next one, 1 to 0. So 1 to 0 means don't care 1. So don't care 1. Next one, 0 to 0. So 0 to 0 means 0 don't care. Next one, 0 to 1. 1 don't care. Then 1 to 1. Don't care 0. Next 1 to 0. 1 to 0 is don't care 1. Next last one is 0 to 0. That is 0 don't care. Right. So this is how I feel. See 1, 2, 3, 4, 5, 6, 7, 8. Similarly J0 K0. See, if I see J0 and K0, that is we have to see Q0. Q0 is always toggling. See 0 to 1, 1 to 0, 0 to 1, 1 to 0 and so on. So what is 0 to 1? 1 don't care, and 1 to 0 is don't care 1. So first one, 0 to 1 means 1 don't care, 1 to 0 means don't care 1, and it will follows like this: 1 don't care 1, 1 don't care 1, 1 don't care, and the last one is don't care 1. Right now, so how many K-maps required? 6 K-maps, but we can eliminate 2 directly. See, if you see the J0, always it is either 1 or don't care. So I can combine all, I can make an octet. Simply I can write J0 is equal to K0 is equal to as 1, because if you see Q0 is always toggling, right? So when the output is always toggles when we apply the j and k as 1 only. So I can eliminate these two k maps. Next we have to go for these two k maps, or I mean 4 k maps for j2 k2 j1 k1. Now so we have to be very careful is, see 000 is 1, but this is 111 110, so we have to come from the bottom. So 001, what is the value? 0 and so on. So how to fill? So 000 is 1 only, and 001 is coming from the down. So 001 0, then 0, and so 3 zeros, 0 0 0, then 4 don't care. So simply fill these 4 don't cares, right? So once we fill like this, what is the combination I can make? So I have to combine this 1 and this don't care. So I can make simply j2 as q1 bar q0 bar. See this one. Similarly k2. What is k2? So 000 means don't care, and the next sequence will come from the bottom. So 001, so 3 don't care. So don't care, don't care, don't care. So 3 don't cares, then 1 1, then again see 3 zeros. So 3 zeros. So again if you see, I have to make this one what you call pair. So again I will get same q0 bar q1 bar, or q1 bar q0 bar. See j2 k2 are getting same. Similarly we have to go for j1 and k1. See what is j1? So 000 means 1, then the sequence will come from the bottom. So 0 2 don't care. So 0 1 don't care, 1 more don't care, right? Then 1 0 2 don't cares, right? So 1 0 2 don't cares. Now here I can make one pair, or using these 2 don't cares I can make a quad. So what is this quad? Simply q0 bar. Yes or no? What is this common? The second one, which is 0, I have to make complement. Next one is k1. So 000 means don't care, then I have to come from the bottom. So don't care 1, don't care 1, then 0, then 2 don't cares 1 0. So 2 don't cares 1 0. So again I can make a quad like this. So again it is q0 bar only. See j1 and k1 same, j2 k2 same, and what is j0 and k0 also same, right? So once we get the minimal expressions, what is the next step? We have to draw the logic diagram. So how many flip-flops? 3 flip-flops. 1 2 3. I can use the positive edge trigger or negative edge trigger. So in this case I am using positive edge trigger. This is the clock, same clock for all the flip-flops. J0 K0 Q0 Q0 bar. So J1 K1 Q1 Q1 bar, J2 K2 Q2 Q2 bar. So these are the outputs. Then we have to apply the inputs. What is J0 K0? Always it is 1 only. So very good. What is J1 and K1? Q0 bar Q0 bar. So from here I have to apply same for J1 and K1 over. Next what is K2 and J2? Q1 bar Q0 bar. So I need one AND gate here. So Q1 bar is coming here, then Q0 bar is coming here, then I can make as input something like this. So this is the 3-bit synchronous down counter using JK flip-flop. Now I told you in the previous lecture we will compare the logic diagram for this JK flip-flop as well as the D flip-flop, right? Now see this logic diagram. So if you use D flip-flop, we have to use external gates are so many, that is the circuit is complex. But if I see the JK flip-flop, here I am using only one AND gate for this operation, entire operation. So that is the complexity difference, right? So that's why we can use JK flip-flop or T flip-flop to get simple circuit, right? But we can use D flip-flop also, but the complexity is increasing in the circuit, right? Now we will verify the functionality. Will it give the sequence as we required, right? So initially suppose all are zeros, the outputs are zeros. Now the moment we apply the clock, so J0 K0 is given as 1, so it will toggle the output 1. So but see initially 0, so the Q0 bar will be 1, right? So 1 is going here, so it will also complement its output, so it also will be 1. But what happens to the input of this one? So this is 1 and previously this was 0, that means it is 1, so it is 1, so 1 into 1 1. So all the flip-flops will toggle the previous state, so it will become as 111. So 000 means I will get 111. Now present state is 111. So before we apply the clock, first we will find what are the inputs. So it is changed to 1, now that means it will change it to 0. So this is also change it to 0. So anyway this is not required. So Q0 bar is 0, Q1 bar is also 0, right? So this is coming here 0, this is also coming here 0. So what is the input of this AND gate, or we can say output of the AND gate and input of the J2? It is changed to 0, right? And also it is 0 here, 0 here. Now the moment we apply the clock, the Q0 always it will toggle. So Q0 is 0, right? What happens? So for J1 and K1 the inputs are 0 0. So the 0 0 means it will maintain the previous state. So Q1 is 1. Similarly J2 K2, yeah, I forgot here. So J2 and K2 will be same, right? So that is a mistake. So J2 and K2, the see here Q0 bar, Q1 bar, Q1 bar, Q0 bar, same, right? So similarly it will maintain the previous state only, right? So similarly we can verify the functionality of this 3-bit synchronous down counter. So I will verify the last one. Suppose the present state is, suppose here present state is suppose 0 0 1, that is 1 0 0, right? Now what will happen when we apply the clock? See, this is 0 means this will be 1, so this is 1 means here 1, so this is also 1, this is also 1. See, 0 means here also 1, so 1 is coming here, 1 1 means 1, right? Now if we apply the clock, what will happen? So anyway this will change its state. So the next state will be 0 to 1, right? So what happens to this circuit? So this is 0 means this is 1, so 1 1 means it will also toggle its output. So 0 to 1. So what happens here? Now here this is also 1, so previous is 1, now it will toggle. So what happens to, so next state is 0. See, so this is the required state, right? So 1 0 0 to 0 1 1, that is the next sequence. See, 1 0 0 to 0 1 1. So it is following the sequence as we required. So we can fill this table something like this. So 1 1 0 means I will get 1 0 1, 1 0 1 means I will get 1 0 0, 1 0 0 means I will get 0 1 1. Similarly 0 1 means I will get 0 1 0, 0 1 0 means I will get 0 0 1. After 0 0 1 I will get as all zeros. So we can verify the functionality as like this, right? So this is about the modulus 8 synchronous down counter, or we can say 3-bit synchronous down counter. In the next lecture we will see modulus 6 counter or modulus 10 counters, that is we have to stop the count in between, right? So 3-bit means it maximum count is 8, but we can stop in between also. So that we will see in the next lecture.